Hi, and welcome back to Weapons of Math Instruction. Thanks for tuning into Day 2 of our Pi Week celebration. If you missed the first video, you could find it either on my Facebook page or on my YouTube channel. In this little bite of pi, we're going to look at the trigonometric functions and take a close look at the unit circle, which I showed you in the first video. In the first segment, we'll look at right triangle trigonometry. So first, what's a right triangle? Well, it's a triangle that contains a right angle. And here's what a right triangle looks like. I've labeled the sides with the letters A, B, and C. I've labeled the right angle with that block symbol that I showed you in the first video. And I've labeled the angle in the left corner with the Greek letter theta. I didn't bother labeling the third angle because I won't need it for my discussion here today. The longest side is called the hypotenuse, and it's the side that's opposite the right angle. So that's this guy here that I've labeled C. The two shorter sides, labeled A and B, are called the legs of the right triangle. And the lengths of the legs and the hypotenuse are related via the Pythagorean theorem. A squared plus b squared equals c squared in this notation that I've used here. And the three trigonometric functions that we'll be looking at in this video are the sine, cosine, and tangent functions. There are three more trigonometric functions, but we won't need those here today. So let's start by labeling the sides of the triangle with the names by which we'll be referring to them, starting with the hypotenuse. Now we're going to be looking at the trigonometric functions of the angle theta. So we'll be looking at this triangle from the point of view of that angle. The vertical leg is the side that is opposite theta. And the horizontal leg is the side that is adjacent to theta. How can you tell which side is which? Just imagine that you're in a triangle-shaped room, and you back yourself into the corner marked theta. When you look straight ahead, you're looking at the opposite wall. When you spread your arms out, they'll be touching the other two walls. The shorter wall is adjacent to you, and the longer one is the hypotenuse. To remember the definitions of the trig functions, we use the nonsense word SOHCAHTOA, which stands for sine opposite hypotenuse, cosine adjacent hypotenuse, tangent opposite adjacent. Break the word up into three-letter blocks, and you can easily remember the definitions of these trig functions, which are the sine of theta equals the length of the opposite side over the length of the hypotenuse, which in this triangle is A over C. The cosine of theta is the adjacent over the hypotenuse, which is B over C. And the tangent of theta is the opposite over the adjacent, which is A over B. Now here's a nifty little fact about the tangent function. If we divide the sine of theta by the cosine of theta, then by definition, that's opposite over hypotenuse divided by adjacent over hypotenuse. We divide these two by flipping over the second fraction and multiplying, and then we cancel out the hypotenuse from the numerator and denominator, and we get opposite over adjacent. But what's this? That's just equal to the tangent function. So we get that tangent is sine divided by cosine. Now, we're already a few minutes into the video, and some of you have got to be wondering by now, I came here for the pi. Where's the pi? Well, it's coming in this segment, which relates the unit circle to trigonometry. And here's our old friend the unit circle from the first video with one small change. I'm only showing the angles in radians. Degrees get the boot for this discussion. After all, the radian measures of the angles are where the pi's are, right? Now, in the first segment, we were just talking about triangles. What do triangles have to do with circles? Well, quite a lot, in fact. We can make a triangle inside the circle by drawing two line segments, one radially outward from the origin and one vertical. We'll do this for the angle pi over 6, right here, like so. And now I've got a right triangle inside the circle with theta equals pi over 6, which, as you may recall from the last video, is 30 degrees. Let's blow up our right triangle so we can get a good look at it. I've drawn it in the xy plane and labeled the corresponding point on the unit circle right here. Let's label the sides with their lengths. First, we know that the hypotenuse is 1. How do we know that? Because the hypotenuse is a radius of the unit circle, and the unit circle has radius 1. And we can get the lengths of the legs from the x and y coordinates of the point on the unit circle. This is the x coordinate, and this is the y coordinate. Next, we'll apply SOHCAHTOA to get the sine, cosine, and tangent of the angle pi over 6. So the sine of pi over 6 is the length of the opposite side, which is 1/2, divided by the length of the hypotenuse, which is 1. And that just gives us 1/2. The cosine of pi over 6 is the length of the adjacent side, divided by the length of the hypotenuse, which gives us the square root of 3 over 2. And to get the tangent of pi over 6, you can take your pick. You can either divide opposite by adjacent, or you can divide the sine by the cosine. Either way, you're going to get 1 over the square root of 3. And check this out. The cosine and sine of pi over 6 are just the x and y coordinates of the point on the unit circle. So going forward, we could just read the values of sine and cosine of any angle off the unit circle without bothering with a triangle. So let's get the sine, cosine, and tangent of pi over 4 using only the unit circle. So pi over 4 is right here. Here are the coordinates of the corresponding point on the unit circle. The first coordinate is the cosine, and the second coordinate is the sine. So the sine of pi over 4 is the square root of 2 over 2. The cosine of pi over 4 is also the square root of 2 over 2. And the tangent of pi over 4 is the sine divided by the cosine, and since they're the same number, we get 1. In this segment, we'll look at the graphs of the sine, cosine, and tangent functions. I'm going to use the unit circle to help me here. Now I want to stress that trig functions are functions of an angle. So this x in sine of x here takes on the values of the angles in the unit circle. The y value, the value of the function, is the value of the sine of those angles. So that's the second coordinate in these points around the unit circle. I've already labeled the values of the angles from the unit circle on the x-axis. Also, as you scan around the unit circle, you can see that the same values of sine come up over and over again. 0, 1/2, square root of 2 over 2, square root of 3 over 2, 1, and their negatives. I've labeled those values on the y-axis. Let's start plotting points. We'll start with the angle 0 radians. The sine of 0 is 0. So the first point on the graph of the sine function is the point 0, 0 right here. Let's move on to the angle pi over 6. The sine of pi over 6 is 1/2. So the next point on the graph of the sine function is pi over 6, 1/2 right here. Let's move a little faster now. Next up is pi over 4, then pi over 3, then pi over 2. And I think you get the picture. So I'm just going to fill in the rest of the points, like so. To fill in the gaps for the angles that aren't on the unit circle, we'll thread a smooth, continuous curve through our points, like this. Now, the unit circle ends at 2 pi radians, but the graph of the sine function doesn't. Once we get to 2 pi, we get back to where we started on the unit circle. And likewise, the graph of the sine function gets back to where it started. From there, it repeats this pattern over and over like this. The graph of the sine function just keeps waving like this forever. For that reason, it is said to be periodic. The period is the space on the horizontal axis that is required to complete one cycle. And that space is 2 pi. Now you can do a similar exercise for the cosine function to get this graph. Cosine is also periodic with a period of 2 pi. And finally, you can go through the same exercise to get the graph of the tangent function. And what's this craziness? The first thing that I want to point out are these dashed lines here. These are called vertical asymptotes, and they're where the tangent function blows up to either infinity or negative infinity. Why would it do that? Recall that the tangent function is the sine divided by the cosine, and so wherever the cosine is equal to 0, the tangent is undefined. This happens at the odd integer multiples of pi over 2. So pi over 2, 3 pi over 2, and then the negatives, negative pi over 2 and negative 3 pi over 2, and so on. The tangent function is also periodic, but it only needs half the space that sine and cosine do to complete one cycle. So its period is pi, not 2 pi. In this last segment, we'll take a look at series representations of trigonometric functions. You won't see the connection to pi in this video, but I promise that you will in the next one. I need to borrow a concept from calculus here, namely Maclaurin series. This is a method of expansion of f of x into infinitely many terms. This dot 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 here indicates that this series continues in this pattern forever. This may seem like a pointless endeavor, but it's not. For one thing, it allows us to approximate functions using explicit formulas in powers of x. The calculus part comes with the primed functions. This little tick mark here is a prime. And we read this as f prime of 0 times x. F prime is the derivative of the original function f, and the derivative gives us the slope of f. This here is f double prime, which is the second derivative of f, and it gives us the slope of f prime. Now after a while, using more primes for higher order derivatives gets cumbersome, and so we say enough is enough and use a superscripted number in parentheses, like here in the third derivative, which gives us the slope of the second derivative. Let's look at the Maclaurin series for the sine, cosine, and tangent functions. Here's the series representation of sine of x. The terms have a nice predictable pattern to them. The signs alternate plus minus plus minus. The powers of x are all odd, and the denominators are all factorials of the powers of x. That makes it easy to see that the next term is x to the 9th power over 9 factorial. Here's the series representation for the cosine of x. It's got the same basic pattern as the series for the sine of x, except this time the powers of x are all even instead of odd. The series representation for the tangent of x is the oddball, which you might expect because its graph is also an oddball. It doesn't wave like the graphs of sine x and cosine x. In fact, there's no easy pattern in these terms at all, and if you want to know what the next term is, you have to work it out using Maclaurin's formula at the top of the slide. But calculating Maclaurin's series is not what I want to show you here. I want to show you visually how the terms in the Maclaurin series combine to form better and better approximations of a function as more terms are included. We'll illustrate this with the sine of x, whose graph I've drawn here. Here's the graph of y equals x, which is the first term in the Maclaurin series for sine of x. It's not a very good approximation to the sine of x, except near the origin where the graphs are close together. Now watch what happens as we add more terms from the Maclaurin series. Here's the graph when we add the second term, and the third, and the fourth. You see what's happening here? The graphs of these polynomials are starting to look more and more like the graph of the sine function, and over a larger range of x. Adding more terms would just improve this approximation. That's it for this video. Thank you for watching, and tune in again tomorrow for another bite of pie. Hey everybody, if you enjoyed this video and want to see more like it, then please do follow me on my socials. You know you want to.